This is the screencast for section 6.3, example 3, solving an initial value problem. So we're going to use integration by parts, as you may have predicted, and then we are given a initial condition for this to be able to solve for C. So solve the differential equation dy dx equals x natural log of x, subject to the initial condition y equals -1 when x equals +1. Confirm the solution graphically by showing that it conforms to the slope field. Okay, so first dy dx equals x times the natural log of x. Well, it wants me to find a solution or solve this, so I need to get the differential dy and then integrate both sides. So the integral of dy is easy, but on the right side here we have x times natural log of x. That is a product. There are variables in those two functions that are being multiplied together. They're not related by a derivative. That clues me into using anti-differentiation by parts. Now I'm going to make u x and dv natural log of x. If I took the derivative of natural log of x, I'd get 1 over x, x to the -1, and I could keep taking the derivative of that forever and ever and ever, and it wouldn't make this problem any easier because one of these functions wouldn't kind of go away or just to a constant. But if I make ux and dv the natural log of x, I would have to be taking the antiderivative of the natural log of x. Do you know the antiderivative of the natural log of x? I don't. So I'm actually going to have to do what it might be opposite of what my gut reaction would be. I'm going to make u the natural log of x this time, and dv x. Again, natural log of x, if that were dv, I'd have to take the antiderivative of natural log of x, and I don't know what that is. Alright, so now let's take the derivative of u. So du is 1 over x dx, and the antiderivative of dv, which is 1/2 x squared. Now let's use our anti-differentiation by parts. So y equals, we've got u times v minus the antiderivative of v again times u. Now you may see what happens here. When we simplify the antiderivative, a x squared in the numerator and an x in the denominator cancel out, and we really just have 1/2 x. So that actually worked out okay, even though it was opposite of what we may have been thinking to start out with. For as far as our u and dv, identifying our u and dv was concerned. So now the antiderivative of 1/2 x dx is 1/4 x squared. And we've got a plus c. Now we've got that initial condition. So I'm going to plug in -1 for y and +1 for x and solve for c, and I get -3/4 equals c. Now of course I'm going to confirm the solution graphically by showing that it conforms to the slope field. So I put in y1 x natural log of x, and if I make the window a standard window and do my slope field program, I come up with an error. Now the issue with the error is, remember, you can't plug negatives or 0 into a log. So what I have to do then is go to my window and give a good first value for it to evaluate. So maybe 0.1. In this case, my x value that I'm using in my initial condition is +1, so 0.1 would be plenty to be able to see if this solution I found would fit into the slope field. Now, let's try that slope field again. There we go. Now I can put my solution with my c value into y2, and I can see that it does fit my slope field very well. Then now try problem number 11. Says solve the initial value problem. Confirm your answer by checking that it conforms to the slope field of the differential equation. Alright, so we have dy dx equals x plus 2 sine of x, and y equals 2 when x equals 0. So the differential dy equals x plus 2 sine of x dx. My goal is to integrate both sides. I have inside my integral on the right a product of two functions that have variables in them. They do not relate to each other by a derivative, so I can't use u substitution. I'm going to have to use anti-differentiation by parts. This is a situation where if I make u x plus 2, and dv sine of x, that would be the smarter move, because if I take the derivative of u, actually du would have only a constant in it, and really if I took the derivative of sine of x, I'd be going forever and ever and ever. That would not benefit me in any way. So u is going to be x plus 2. dv is sine of x. The derivative of u is dx. Then the antiderivative of dv is v equals negative cosine of x. So y equals the antiderivative of dy, x plus 2, so u times v, minus v times du. Now those two negatives can, the one negative on the inside of the integral can come outside, and I have a plus the antiderivative of cosine of x, which is a very easy antiderivative for me to do. That would be sine of x, and then of course plus c. Well, now I can plug in my initial value where x is 0 when y is 2, and then solve for c, and I get that c equals 4. So my solution that also satisfies that initial value would be y equals negative cosine of x times x plus 2 plus sine of x plus 4. Now the domain of this slope field is not limited, so I don't have to worry about setting my window like I did last time. A simple zoom 6 would work just fine. So putting dy dx into y1, graphing my slope field with the solution in y2, I can see that my solution does fit the slope field nicely.